So step 5 is we have to find what we're asked to find. And we've been asked to find the voltage for all time. We've done that. We're also asked to find the current for all time, and we haven't done that. So let's begin with this. There's 2 time regions, time less than 0 and time greater than 0. So the only way to figure this out is to solve for each time region. Now, for time less than 0, it should be easy. That just looks like DC steady state, right? We can redraw that for time less than 0, and it should be pretty easy. We've got this capacitor. Of course, now we can eliminate that capacitor if we want to, because all we care about is that current for time less than 0. And for time less than 0, that switch is connected. And we've got 9 amps being pushed through the circuit. So we only care about our I, so we can get rid of this part. And we've got 6, 4. We've got our I. Always important to draw what we're trying to find. If we don't draw what we're trying to find, we're probably going to simplify it away. And then there's no telling what we're going to solve for. And so we have this circuit. And when I look at this circuit, I can see that these 4 and these 6 are in series. So I can simplify it down to 10, 8, 9. And again, look how careful I've got to be about where I draw this I. If I make a mistake and draw the I this way, it's wrong, because this I comes before the 8. I have to say it's in this direction. And I haven't destroyed anything by combining these guys, because these are outside the I. What I said is I'm going to simplify everything to the left of those 2 points. There's only 2 things that I'm simplifying. All the current through one has to go through the other. And so I haven't destroyed anything. All right, so now let's get back to what we have here. We need to find I. This is just our current divider. And our current divider says that the current I is equal to our source times, let's see, I is through this 10 ohm, right? So it's times the opposite one in the numerator over the sum. And this current is trying to force current in the opposite direction, this current source. So there's a minus sign in front of it. If this current source was going down, if it looked like that, then I would be equal to positive 9. But since it's forcing it the opposite way, there's a minus sign. And so we get, let's see, minus 9 times, let's see, 8 over 18. Let's see, 9 goes once, goes in twice here. 8 over 2 is minus 4. So we know it's minus 4 amps for time less than 0. So I'll write that up here. For time less than 0, I equals minus 4 amps. And that's the first part to our question. Let's now find the second part to our question, which is what's going on for time greater than 0. Now I've made this problem longer than I would ask on a test. I wouldn't ask you to find both the current and the voltage in 2 different regions of time. But this covers all possibilities. This is what I would probably ask on the test is, firstly, if I was asking a simple first order problem, it would just be the part on the left. If it was the more complicated problem, I would probably ask for what is this current for time greater than 0? Now, for time greater than 0, we got to draw the whole thing because stuff is changing, right? That's supposed to be a farad. We've got 6 ohms here, 4 ohms here. And this switches down, so we don't have to draw what's to the right of it. 8, and we're trying to find this current. Okay, there's a few ways to do this. Probably the simplest way is to say we can combine the 4 and the 8. Now, You might feel uncomfortable with that because doesn't that destroy the I in between it? And the answer is no. I could just as well written the I over here. And now we can simplify everything in here without disturbing our I. So let's do that. We've got our capacitor, 1/16 farad. We know what that V is. We figured it out down here. We've got our 6 here. We've got our 12 over here. And we want to find out our current here. Now you might be tempted to put these 6 and 12 in parallel. They are in parallel, but if we do that, we're going to destroy our I. Again, it's so important to keep a record of what we're trying to find. If you don't draw this, you're going to combine this, and you're going to find I someplace else. You'd end up finding your I through the combination of this thing, which should be the current through here, not what you want to do. So, man, this looks almost like a current divider, doesn't it? Except that we don't know what the current is here. We know what the voltage is here. But that's beautiful. If you know what the voltage is between this point and this point on the capacitor, that's the same, because it's connected by a wire, as the voltage between this point and this point. And because it's connected by a wire, it's the same as the voltage between this point and this point, which means it's the same as the voltage between this point and this point. So you know the voltage across the resistor. So if you know the voltage across the resistor, you can now find what I is. By Ohm's law, it's equal to the voltage across the 12 ohm divided by the resistance of the 12 ohm, which is going to be, we already found what that voltage is over here, 24 e to the minus 4t divided by the 12 ohms. So it's going to be equal to 2 e to the minus 4t amps. And that's what it is for time greater or equal to 0. So now we can find the last part of the equation, the last part of what it was asked to find, which is I of t is equal to either minus 4 amps for time less than 0 or 2 e to the minus 4t amps for time greater than or equal to 0. And this plus this is the entire answer to the problem. But wait, you might ask. Here, the voltage is continuous, right? If we look at time less than 0, it's 24. If we look at a time equals 0, we plug in 0 for t, we get e to the 0, which is 1, and we get 24. That checks out. This doesn't check out. If we plug in time less than 0, we get minus 4. Plug in time 0, we get e to the 0t, which is just 1. We get 2 amps. So it jumps from minus 4 amps to 2 amps. We did something wrong, right? No, we did everything right. The rule is the voltage across a capacitor is continuous, and it is, but everything else can change instantaneously. So this current did change instantaneously. For time less than 0, it was actually headed in this direction by 4 amps. And then at time greater than 0, it instantly moved to the right and became 2 amps. And in fact, if we were to graph that, we weren't asked to graph it, but if we did graph it, it would look something like minus 4 out here, and then instantly jumping up to 2 here and decaying down. And it had been minus 4 forever. So this is the graph of the current through that 4 ohm resistor, as opposed to the voltage across the capacitor, which has to be continuous. So there we end up with 24 for time less than 0, and then it smoothly decays away down to 0 for time greater than 0. And sure enough, it's always continuous. I can draw this without ever lifting the pen from the paper. Okay, that's problem 3 in minute detail.